Good afternoon, everyone. Today's seminar is the seminar of Filippo Mastropietro, and he will talk about Berger's classification. So you can start.
Hello, everybody. Welcome back to Semiva. Thank you, Letizia. Today we'll talk about holonomy group of Riemannian manifolds. Holonomy is essentially an algebraic invariant associated to a connection on a manifold. We will answer to a question, which is the question, which groups arise as holonomy groups of certain manifolds? And this is important in connection to Calabi's conjecture, and we will see this conjecture in this talk together with some stuff. This is the structure of the talk. In the first part, we talk about connections in general, and I define holonomy. The second part, I introduce Berger classification and what I call some nonsense. I will explain what I mean. In the third part, will be more geometrical. The third part will probably have a break in between the second and the third. The third will be a bit more technical and geometrical. It will be about a tool called principal G structure, and I will talk about it and why I chose to talk about them. So, okay, the first part we'll see connections were already introduced by Letizia, if you don't know what it is. We will see a more geometric point of view on connection and the interpretation of parallel transport. And we introduce holonomy again. Now, Berger classification, again, is the answer to which groups arise as holonomy groups of manifold and which don't. What's really the nonsense? Since, of course, we don't really have the time to discuss all this group, all the group that we will need, the nonsense is that we will be a bit philosophers today, and I will just explain in some sense who they are without too many details. So this is the nonsense part. Principal G structure is about really understanding the geometry of holonomy. Okay, so up to here, it will be more not too technical, just definition. And in order to explain how having a special holonomy group actually affects the geometry, we will learn about this tool. This is a tool that I believe it's pretty interesting because it's very common in the physics literature to talk about principal G structure and holonomy, and less normal in geometrical mathematical literature. So I think that maybe this part will be appreciated by geometers, and maybe it will also be useful one day. But I believe that the one who don't come from geometry will not appreciate this much because it will get abstract pretty soon. Again, we will not need to know everything about the groups. You don't need to memorize everything I will talk about the groups here. What is crucial as this part is that we'll understand Calabi's conjecture as a statement about holonomy. This is the really important part. So if you don't come from geometry and you feel like you might get lost in between here, just try to grasp this part, which will be actually the end of this section. This is what will be actually useful for understanding better David's talk, this relation. And again, if you feel a bit lost in this part, maybe because you're not from geometry, the really important thing that we'll see here is actually how to interpret the Kähler and the Ricci flat manifold as a manifold with special holonomy. So these are the things that are actually more important for the rest of these seminars. And you just need to focus on this, and just if you get lost in between, it's not necessarily terrible for the rest of this seminar. So the references to this talk will be mainly this one, Dominique Joyce. It's a nice book, which is called Compact Manifolds and Special Holonomy, with Special Holonomy. Most of the talk is taken from here. So again, I think it's good to know for geometry, if you haven't wondered something about understanding holonomy, maybe you can look there. Actually, if you may be working with some strange Calabi or Kähler, that's a good reference. And then there is also this set of lecture notes by Moroyan, which is helpful in understanding better the Kähler part, when we will specialize a certain point of Kähler manifold and the relation with holonomy. Again, this is pretty good. Lectures on Kähler geometry, it has been helpful in writing a part of this talk. And these are most important ones. So let's get started. Let's start from connections. Letizia already told this. I will recall a connection on a manifold M is a map from the tangent space, two copies of the tangent space to a tangent space, such that in this entry below, if I fix one of the components, I leave this one free. This is C infinity of M linear. And if I fix from X to vector field, if I fix the other component, which is just R linear, but it satisfies a Leibniz rule. So if I have this, I have X, F, Y, irreducible function, this is actually F double X, Y, plus X of F times Y. Here F is a move function and the other vector field. The only remark, not just these stupid things, but it's a use different notation for the tangent space, which is this one. I use this one, they're the same things. Okay, just to avoid possible confusions. Okay, so what do we understand? The first part, again, is about understanding this definition in a better way. So what do we understand from here? We understand that in some sense, we are differentiating vector fields with this rule. This is an abstract rule for differentiating. In the sense, I take two vector fields, it's like I'm differentiating in this expression X. This expression here is like I'm differentiating Y in the direction given from the vector X. This is a differentiation in an abstract sense because this is a Leibniz rule. So algebraically, one used to talk about abstract differentiation, derivatives, if one satisfies Leibniz rule. Now, I want to understand the geometrical counterpart of this definition. This is pretty arbitrary to me, at least. So why do we call a connection, for example? It's called a connection because it reflects the fact that it can connect the tangent spaces on two different points on the manifold. And this is the geometrical counterpart of what we will understand. Okay, so let's take a smooth curve. This is a smooth curve. And we have an operation for covariant derivative. Now, this thing here is the tangent space restricted to the curve. Okay, defined in the following way.
Filippo,
Okay.
I have a question. So maybe a general question. So can we extend this notion of connection to any fiber bundle? And
Any fiber bundle, we can extend it to all vector bundles. Of course, Letizia already told about it. We can extend it to some bundles. We'll see later how to extend it to principal bundle. Okay, but to any fiber bundles, it becomes much more complicated. We will see the extension to principal bundles, at least, so bundles with G groups as fibers. I know about these, not general fiber bundles. I'm not sure about those, actually.
Okay, thanks.
Okay, great. So we have operation called covariant derivative, which is defined in the following way. If I have a curve and I want to derivate this vector field X, I just take covariant derivative in the direction of the tangent to the curve. Okay, so it's just covariant derivative. I'm just specifying that the direction will always be the one tangent to the curve. Okay, called again covariant derivative. nothing special. I'm really just restricting our connection to a curve. Now, this is the key tool to talk about parallelism of vectors. Why? Because we are interested in this condition. Okay, so. Definition. Here B is a vector field along gamma, which is just a vector field which is supported just on gamma. Okay, definition. This is parallel. Its covariant derivative is 0. So we're saying if we differentiate in the direction of the curve, this is 0. So this is nonsense constant along our curve. Okay. What we want to do is doing the following. In order to connect different points, the tangent spaces of two different points of a manifold, we'll connect them with a curve, take a vector at the starting point, and we will see that there is a parallel transport. So a vector field which is parallel and which ends in the other point we want. So we use this to transport vector. What's the point? The point is the following. Let x1, xn be a coordinate system, local, on the manifold. Gamma in this coordinate is written gamma 1, gamma n of t, and our vector field is written as components. The xj. Okay, so vectors are this component is just a basis of the vector field given by the tangent direction, okay, to these coordinates. Then one can check easily that this condition is equivalent to the following. Equivalent to a condition on the derivative of these components. So minus Vj of t gamma prime y nobla k I j gamma di t. Now, two things here. First, I'm using Einstein convention. So when I repeat the indexes, j and I, I'm implicitly summing over them. So this is actually sum of between I and j, okay? Second thing, who's this term? These are called, okay, the other are more or less clear. These terms are called Christoffel symbol. We will not use them in the following, but they are defined by this expression. They're just obtain differentiating the vector of our basis. Okay, this expression is very easy to check. It just follows from the properties of the connection. Okay, and the stuff. So this is equivalent to the parallelism of the vector B. What's the key point? The key point is that this is a system of differential equations. The key point is that you can actually solve it in order to construct a parallel vector field, whatever our initial data is. So we can use this to construct parallel vector field. So what we want to say is we have a theorem. Okay, we have a curve. Let's say from T0 to T1, parameterize this through time. We have a vector which is tangent at the first point. Okay, in the tangent space of the first point on the curve, then exists a unique vector field along all the curve, such that T0 is V, this T0 is V, so it's third, okay? And it's parallel. There is a unique parallel extension of this vector here, okay? So proof just reduces to proving existence and unicity of this system of differential equation. Okay, so this is actually a linear system of differential equation with the right constraint. Okay, because we have the initial data set. So my general theory of this that system there admits a unique solution. And it's done. It's okay. Using some relatively elementary tool, we can always construct this. This is called parallel transport. We'll arrive in a minute. This operation of taking a vector in the tangent space at a starting point and prolong it along a curve. So, definition. This construction induces a linear map. P gamma starting time and ending time from the tangent space to the starting point, the tangent space to the end point. This is linear. It is called parallel transport. So this is the main point. Now that we know how to differentiate vector field, we have a rule for transporting vectors along our manifold, just by solving that differential system of differential equations. This is the key point. Now, this is to me the geometrical interpretation, because this gives more sense to the term connection, but it also gives more sense to the understanding of the differentiation of vector field and why it's so important. Because we see in a second that this notion of parallel transport is actually equivalent to the notion of a connection. So we define parallel transport starting from covariant derivative, so from connection. One can also do the converse. So we have a theorem. We have a manifold, a connection on the tangent space again. Vector fields and a point. Then we have this expression with the notation before. We have that the covariant derivative of P can actually be understood as a rapporto incrementale, come si dice in inglese, as this limit for the time that approaches 0 of the parallel transport of epsilon in gamma di P minus epsilon in P on T. So this is actually a derivative, is the limit of this term. Now, since we these two things, y in P and y in gamma di T lives on different tangent spaces, okay? But now, since we transport it, they live on the same tangent space, the one at P, so we can construct this operation. And so covariant derivative is actually this limit, so it's actually a derivative. The proof is pretty simple. It's constructed like this. If I is a basis, I didn't say who gamma is, I'm sorry. Gamma gamma is what is called the integral curve of x. This just means that x gamma t is just the derivative. Okay, that is the unique curve for which x is always tangent. Okay. Definition is pretty. The proof is pretty easy. Because if I is a basis of EPM, then I can just move them along gamma by parallel transport. So AI is the parallel extension at any point, the curve. Then one check in a second that this expression is actually equivalent to just the derivative of the component of my field. Okay, this is pretty straightforward. And this is clearly equal to that second term because of this. That is, since these AI are now parallel, if I parallel transport, I'm just really moving the coefficient because these are always constant by parallel transport. And if I differentiate, I'm really only differentiating the coefficient. So when you see this and you plot it there, this is almost straightforward, since I'm also computing that limit on the coefficient, really. Okay. So this is really to show that indeed these two concepts are equivalent, and a connection is really just about having a rule for connecting different tangent space. And it also gives another nice tool, which is a way of speaking about parallelism, which of course in an abstract manifold is not given a priori. So before moving on, just record this theorem. It's already told you about it, but we will need it in the sequel. So this is sometimes called the fundamental theorem of Riemannian geometry. It's about the existence of a Levi-Civita connection. So if I've got a Riemannian manifold, then there exists unique connection, nabla, such that we have this condition, which is called compatibility with the metric. And that it is torsion free. So this stands this object here. Is zero. So with these two conditions, there is only one connection called the Levi-Civita connection. Okay, it's already told you about it. Now that we know a bit more about the meaning of connection, we can a bit understand these things here. Okay, when I say it is compatible with the metric or a connection, I basically mean that when I move the metric around the manifold with parallel transport, this remains the same in some sense. So even for if I have an orthonormal frame, I can parallel moving it and it stays orthonormal all the time. So this is really what compatibility means in this context. While being torsion-free or symmetric is a more abstract notion, we will not really see what it means. It will remain technical for us in the next. Now that we saw these preliminaries, let's define what holonomy is. Now, a general connection carries some geometrical information, and in this talk, we'll try to understand which information it carries. The first thing that we can do is associate to it an algebraic invariant. This is holonomy. So, a manifold. Now, a connection. Here, all connection will be on the tangent space, if I don't specify otherwise, so it's implicit. We have a point. We say that a curve is a loop It's clear. What this means is a loop based x gamma di 0 equal x equal gamma di 1. Very simply. Now what happens? The parallel transport map now becomes a map from the tangent space of x to itself. This is clear. Now the point is that this map is injective. It's actually invertible. It's invertible because there's unicity to the solution of the system of differential equation. So it can't happen that two different vectors collapse on the same vector. So it's injective and henceforth it is invertible. These maps then belong to the invertible matrices on the tangent space. And with this, we can define the holonomy in the following way. The holonomy based x is what? It's just the set of all these possible matrices. So for every loop, we just consider all these matrices. So for a loop, we consider all these possible parallel transport map. And this is actually turns out to be a subgroup of this set here, the transformation of. Okay, so we take all such things. These turn out to live inside here because it's invertible and it acts on the tangent space. And it turns out to be a subgroup. We want really prove it, but of course it's just about understanding composition of loops at a group operation, which anybody who has seen fundamental groups in his life can more or less understand how it goes. So, one prove it, but it's not only a group, it's actually more, it's what it's called a group. So theorem. This definition is a group. The group, for those who don't know, is just a group with a structure of a differentiable manifold, and these two structures are compatible in the sense that the group operations are smooth. Okay, so now we are finally understand what holonomy is. It's just about understanding parallel transport along any loop to our manifold. Now, again, Berger theorem is about understanding which groups are actually holonomy groups and classify them. So, in order to arrive to Berger classification, let's start to understand who these groups are. Surprisingly, there's a special role in this classification played by division algebras. Division algebras are algebraic objects, which are pretty natural. So, real division algebra are division algebras, are algebras over the real. Such that, morally, we're just saying that division is possible on this algebra. So, such that for all A and B, there exists a unique X, such that AX equal B. Okay? This is our definition of what a division algebra is, just real algebras for which we can actually divide things. A surprising fact is that there's really few of these. So, with decent algebraic properties, we only have 4 possible cases. So in dimension 1, so one-dimensional algebras, we have the real numbers. This is more or less straightforward. This dimension is intended as vector spaces, if you're wondering. In 2 dimension, of course, there are the complex numbers. 4 dimension, in 3, there's nothing. That's an interesting part. There's no real division algebra on 3 dimension. 4 dimension, these are quaternions. Which you more or less all know about, more or less, just 4 dimension, just like complex space for 3 imaginary units instead of just 1. And in 8 dimension, you all have heard, although nobody really know how to define the octonions. Okay, so we have higher dimensional generalization of complex numbers in some sense. We won't really define who these are, unless I assume that you more or less know. These are in some sense the only one, because they are only one with some reasonable assumption. These are the only associative. Okay, I just arrive up to quaternions. There's no more associative real algebras. And this is the only alternative, which means this equation is a weak version of associativity. Okay, those parentheses can move in that way in the multiplication. So there are no other with this very reasonable assumption. Otherwise, I need to relax also this one. The surprising thing is that all these algebras are deeply connected to holonomy because their transformation groups, so groups on, let's say, vector space, not really vector space, on these things, groups that act as transformation of this vector space over this one. Let's define. Now we will define all these special groups as group of transformation of these things. Some of these is already known to some of you which have some familiarity with groups, but it's probably better to explicitly tell who they are. So the first one is well known. We have the orthogonal group. And we know who it is. It is made of matrices such that the transpose metric acts like the inverse, okay, in real coefficients, okay? We have its complex analog, which is the unitary group. Okay, it's very similar. These are matrices with complex coefficient, for which if I take the transpose and I conjugate, this acts like the inverse. Then we have a group that some of you might not have already seen, which is the symplectic group. This one is a bit more exotic. There is more than one definition, not equivalent of symplectic group in the literature. So maybe you will see sometimes something different also called a symplectic group. There are many ways of seeing it. As matrices on the quaternions, such that these same things work. Conjugation or a quaternion is the same as complex number. You take every time you have an imaginary units, you change the sign. This conjugation also for quaternions. So this makes sense, but of course it's still pretty mysterious. But it's a really important group, and it has actually some role to symplectic geometry, and to what we will see later. And it will also be important the determinant one analog. So we have the special orthogonal group as matrix in n, determinant 1, the special unitary group is clear. Then we have, the main point is that determinant don't behave well on quaternions because they're not commutative. So it doesn't really make sense to consider the special symplectic group as the one of determinant 1. So there's a more abstract construction of this. This group is this one, quotiented out with respect to a Z2 action. Okay, so we see, okay, these groups are not the most important ones, so we'll skip a bit. Okay, since it doesn't really make sense to talk about determinant, there is another group which is morally has the same role of having determinant 1, in the sense that it's behave in a good way, but it has a more mysterious definition, of course. And we'll just, this is the special symplectic group for us, and we'll not say much about it. So this is very important. Now, we have left the octonions we have left them behind, because they also have two special groups. Now we have two groups for each of these coefficient fields. Okay, so you have two real groups, two complex groups, and two quaternionic. You have also two groups for the octonions, but they are really ugly to define. So I just say something very, very general about them, which is not totally satisfying, but we'll see that we're not really interested in that. So I just want you to know that they exist. There's a Wien group that is called spin 7, which is a special group of automorphism of R8, okay, that fixes special form on it. Now this form is more than one blackboard long if I write it to you, so we will forget, and we won't learn anything really valuable for today, so I won't write it down. And there's also G2, which is more or less the same thing, automorphism of R7 fixing a special reform. The point is that, okay, we don't say more about them. They also can be interpreted with some effort as some special groups acting of the octonions. So they're also related to division algebras, but that's all that we will say today. And so the point is that these are actually the groups that appears in Berger classification. So they are the more or less the only groups appearing as holonomy of this class of manifolds that we will see. So what's the point? Now the point is the following. Berger section is a theorem of 1955. The point is you have a manifold M, which is Riemannian, simply connected, which you know what it means. It is irreducible. We will see what it means, but it's more or less clear. And with this condition, we'll say more later. Non-symmetric, we'll see later what this means. Then, the holonomy group of the Levi-Civita connection, set to the matrix, is one of the following. The first possibility is the special orthogonal group. Then, in all even dimension, we have the unitary group. This is the group of Kähler manifolds, we will see. So manifold with this holonomy Kähler. Again, in even dimension, we also have the possibility of having a special unitary group. These manifolds, we will see, they're Calabi manifolds. They actually Ricci flat and Kähler. This is really what they are. Calabi can depend on the definition, so I'm not really saying it's Calabi. These are Kähler and Ricci flat. The fourth group is for manifold whose dimension is a multiple of 4. And of course, in this case, we have the symplectic groups. These are interesting manifolds. These are called hyperkähler manifolds. Which we won't see today. Maybe later on, we're not still very sure about it. But these are a nice, very nice class of manifolds that maybe we'll learn something in later talks. Again, in this dimension, we also have a manifold whose group is what I informally called the special symplectic groups. These are called quaternionic Kähler. which is pretty exotic manifold, but exists in the interest. And then we have the most special cases. Only in dimension 7, there are manifold with structure with holonomy group G2, and only in dimension 8, we have manifold with holonomy spin 7. That's the main point. These they don't have really any. These are just a further exceptional holonomy because they're pretty rare. Okay, so each of these situations defines a really special geometry, really special structure that there is on a manifold, and we'll see something about Kähler and Riemannian Kähler. The rest are still pretty interesting. Maybe we'll see something about hyper-Kähler, maybe not, and the rest we won't see actually anything. This one are also pretty pathologic, so we're not really interested in that.
What does non-symmetric mean?
No, I will say it. We'll take still a few minutes. I will make some little remarks on what this theorem is telling us. I will say what non-symmetric is, and then we'll do a short break. Okay, I'll arrive to it, of course. Now, for now, okay, we don't know what that assumption means. Essentially, non-symmetric just means the symmetric manifolds are one for which holonomy is actually computable with some ease. And so they are a class of manifold which is totally classified already. So it was not really interesting for this at Berger time, because we already know since Cartan time. What?
The definition of symmetric.
No, it's not, but they're totally classified. And you can compute, they have a special algebraic structure that allows to compute holonomy with these special algebraic tricks, which are impossible on general manifold. The notion of holonomy is analytic in essence, but for this manifold, you actually reduce it to just some algebraic computation. And you learn that for those, it's something computable. For all the rest, it's much, much harder to understand who the holonomy is, because there's no tricks like this. And it becomes a pretty difficult analytical problem to understand holonomy. This is the content of Calabi's conjecture and what Davide will show next week. The moral is this: symmetric are space for which we can compute it with algebraic trick. All the rest is a mess. The point is that Berger really only stated... Exactly, and we will see it in a second. The point is this: Berger only proved that these are the only possible groups, but he didn't show that there exists manifold with such holonomies. Okay, so for many years, it took many years to find examples of such manifold. Okay, and this is also what is really interesting about Berger classification, because it really guided our intuition of which manifold might exist despite being pretty exotic. So it was really helpful in understanding, in formulating Calabi conjecture. And in fact, the existence of manifolds with holonomy SUM has been proved by Yao after a conjecture again of Calabi, and this is what Davide will talk about. We will not really see it, but Calabi's conjecture and its solution also allows to construct the first example of hyper-Kähler manifold with similar ideas. So this is pretty important. Before, there was no example, of anything below this level. Okay, and the first attempt, Calabi and Yao together gave the first example. I need to say on compact manifold. There were some examples of compact manifolds, but on compact one, the first results were found by Calabi and Yao, and these later on. But eventually, we found out that all these actually appear as holonomy. Okay, so another important part is this. You have seen what the rich tensor is. And you can understand that Ricci flat manifold is one for the Ricci tensor vanished. Okay, pretty simply. The fact, which is really important, is that all these group are all groups of Ricci flat matrix. Okay, okay, that's not Ricci flat matrix. So this is really about understanding this special condition. Ricci flatness is strictly related to holonomy, because every time you have these special holonomy groups, not really always, but very often, you end up with Ricci flat matrix at a certain point. This will be important, of course. Now, let's do a quick introduction to symmetric spaces. Actually, I actually wanted to do a full section on this, but the seminar became really too long, so we'll just be very quick on what they are. So the point is this. Let's look at the hypothesis. Okay, simply connected is okay. There's no, every loop can be contracted to a point. Irreducible just means that even at a local level, it can't happen that the manifold splits as a Cartesian product and the metric splits as the metric product. And it's more or less clear, I believe. Now, symmetric is the most special one. So I will not give the proper definition, but morally, they are manifolds of the form M equal G over H, that is, they are the quotients of two Lie groups. So G Lie group, H closed. Okay, it's not a definition. I'm not really saying who the metric is of such a space, but morally, they are the space that can be constructed on this form with a canonical metric, and I'll just skip this part a bit. So this thing is a manifold. If you quotient a group for the other, you don't have a group if it's not normal, but it's still a smooth manifold if the group is closed. This is more or less the point. You can see that they have a special algebraic structure. There is a special action of G. The main point is the following. We'll let this so that we can keep Berger classification for some minutes. Okay. The main point is the following, that if you choose G and H properly, it's not given that one M is given by a unique G and H. There can be more. Okay, so if you choose G and H properly, then the holonomy then is exactly H. Okay, this is the main point. Again, we can say more about it if you're curious, but it will take not too much time, but I want to arrive to another thing first, so we'll see it later eventually. The main point so is that with this construction, we can construct a lot of examples of manifolds with special holonomy. And the main point is that symmetric spaces has been already classified long before Berger conjecture. By Cartan, it works between 1925 and 1927. The point is, okay, studying them becomes a problem in Lie group theory. The groups are complicated, but we know a lot about Lie groups. So with a lot of patience and the genius of Cartan, we can classify all of these with all possible configuration, and so we can also classify all the possible holonomy groups. So the main point is that this construction, a lot of groups appear as holonomy groups because it's a pretty free construction, just taking quotient with right groups. Okay, but still, okay, these are all known. By Berger time, it was known what happens on non-symmetric space. And again, the moral is one I said before. This one, for this reason, have a lot of tricks that can help you computing holonomy. Okay, this one are totally no tricks. It becomes a fully analytic problem and a really hard one. And this is what, again, David Stork will talk about. So the last thing I want to say is the following. which is an important remark. Symmetric spaces are never Ricci flat. So we deduce two things. One is that I say that a lot of groups arise as holonomy groups of symmetric spaces, but not the Ricci flat one. So there's no chance for SUM, SPM, and G2, SP7 to appear as groups of symmetric spaces. No chance at all. That's an important point. And again, this made us more or less understand that Ricci flat is really a peculiar condition in geometry, and it's really rooted in holonomy theory for some sense. So again, now we'll stop for a break, we'll make a break, but again, last anticipation of David's talk, this is really the condition we will focus next in his talk, and so from now on. Okay, now we'll make a break. What I will tell you about in the last section, now we only stated theorems and definition and blah, 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 and so on. In the next section, we will learn how restricting holonomy groups, so special holonomy groups such as UM and SUM, really affects the geometry. So we will substantially see a general theory, G-structure, which I believe is pretty interesting for geometers, and we will prove how these imply Kähler and these imply Ricci flat Kähler, which is the most important and one of the important things of this seminar. Okay, we'll recover after the break. Okay, everybody, we'll get back. This last section is about understanding, again, how restriction of the holonomy group affects the geometry. So, to understand it, we need to understand a bit more of Lie group theory and the action of Lie groups on manifold. So there's this notion which is pretty important, which is M is a manifold. G, Lie group. A principal G bundle, we will omit principal for shortness, is morally just a vector bundles with fiber Lie group instead of vector space. So a manifold was a projection. We have an action of the Lie group G, which is free on the fibers of P. And the fibers of P are the geometries. It is just a long definition to say that it's the same thing of a vector bundle, but the fibers are Lie groups instead. Okay, nothing more. This is the key example, and the only one that we'll see properly, which is called frame bundle. Can be constructed for any vector bundle, let's say for the tangent bundle. And the tangent bundle, this is just this set. Points of the manifold and the basis of the tangent space. That is, M is a point on the manifold, is A1 AM are a basis of EM. Okay, so this is just the set that defines this frame bundle. The projection is obvious. Here, M6. Okay, so this is the set. The projection is obvious. What is more or less clear is that there is an action of the set of invertible and dimensional matrices. Acts on it, and one realizes that it is indeed a GLMR bundle. Okay. Of course, it acts because if I have a basis applied for an invertible map, this is just the action, actually, and this is not a bundle. Now, the main point is that you can define connection on such things. So, definition. Given a G bundle, given a G bundle, a connection D on P is a vector subbundle D of the tangent space of P. Okay, so we take the tangent bundle at P, not at our manifold M. We take a subbundle of this tangent space such that P is G invariant, and the tangent space at any point P decomposes as this space. So dP is our subbundle. Okay, GP is equal to the kernel of the differential of the projection. Okay, so we're just saying this is the same thing as the tangent space to the fiber at P. Okay, we're just saying take the tangent space and give a completion of this. Choose a favorite completion, and this for us a connection. So I leave you wonder a bit on why this generalized notion of connection in a good way. And for Krishna was before, this also give more or less the idea behind defining connection on fiber bundle in general. Okay, it's about this splitting on the tangent space of the bundle. Okay, now the main point is that we can pass from frame bundles to bundles in the following way. There is this equivalence. So assume that we have a G bundle in general for now, but the example that you have to keep in mind is the frame bundle. We have a general G bundle, and we can construct, associated to it, a vector bundle. And if there's a connection here, we'll have a connection on that vector bundle. So the point is, fix what is a representation on some vector space of this group G. Right? And what you do from here? G acts on P times V, the vector space, in this obvious way. G P V equal G times P from PG times P. Okay, it has a natural action on P, and the representation gives an action on P. So there's this action. We define this bundle, which is indeed a vector bundle, by taking quotient. We take this product with quotient by G. We have a projection on P over G, which is clear. And this is actually isomorphic to M by the definition of G bundle. We just quotient on the fiber, so our manifold comes back, of course. And this turned out to be a vector bundle with fiber B. So this is instantly clear, but the point is that since this G action is free, the fiber is indeed V. There is a quotient, but the fiber remains isomorphic to V because the action is free. That's the main reason. And this gives a one-to-one correspond. The point is this, okay? If I have the natural representation of GL MR on an M, this is natural, it's just multiplication of the matrices. Then its associated bundle is a tangent space. That's the point. Once one proves this, one can realize that there is a one-to-one correspondence between vector bundles with fibers on V and a correspondence between principal bundle with fibers, the invertible transformation on D. That's more or less the philosophy. Okay. In the same way, one can realize that there is a one. This is not too important. Now, the main point is the following. I think I'll omit this since we are going pretty long. I sketch the construction for which one can construct a connection given the connection. If I have a connection on P, The point is that on E, which is again the quotient, which is now a vector bundle, can induce a connection here. The main idea is to take a section. This thing lifts to a section of this type from V to V. Okay, this is G invariant, which is G invariant. Okay, since these are all quotient by V, by G, I forget the quotient and I have a G invariant section at this level. And the main point that this is then, okay, P times V and then projected to V. Very simply, if I take the differential, this is a map from the tangent space of P to V, essentially. So a section of V time of this, okay, over P. Is 0.5. If I have this construction, then V has a decomposition given by the connection, okay? I just apply this decomposition. So V, the tangent space of the composition, P of P decomposes because we have a connection. And so I just project of this component. Okay, I project this thing, I project it, and I obtain a map to these things, V tensor P of D. But one can see that D is indeed the pullback tangent space. Okay, it's to a tangent space. So these actually become a section of V tensor V's, which is G invariant. I can quotient by G, and this becomes a section of A times this star M, and I obtain a map that takes a section like this to a section like that, and this is by definition the connection. Okay, a connection can also be seen as a map that takes a section. I skip you on some details, but can be seen as a map that takes a section like this, and a section like this. So this is, and I, of course, I'm skipping many details of this. And the main point is that this construction allows to create a one-to-one correspondence between connection on the tangent space, in particular, to connection on the frame bundle. Okay, this is more or less the construction, and one just has to work out all the details. But this is the main point. There is a one-on-one correspondence between connection on PM and connections on the frame bundle. Okay, this is the main idea. Using this, we can restate our statement about holonomy in this language of principal bundle. And this is very important because it allows us to define what is called a G structure, which is a useful way to think about structure like Kähler, Riemannian matrix, Nickel matrix, and all of these. So this is the main theoretical tool. G structures. G now will be a subgroup of the matrices. Dimension n. Okay. Then G structure on the manifold M is just a subbundle P of the frame bundle with fiber G. I'm just taking a sub-bundle of this frame bundle with fiber as this given group. Okay, and this is where we are going. The main point is that geometrical structure are often equivalent to behavior. Consider this example. If you have a Riemannian metric, then you're allowed to take orthonormal basis. Take the set of orthonormal basis of yeah. This is a subbundle of F of the frame bundle. Who is the fiber? They are matrices, okay, which rows are an orthogonal basis. They are orthogonal matrices. So this is an ON bundle. It's a bundle over the orthogonal group. And the converse is more or less identical. If I have an ON bundle, I just these bases that we say they are orthonormal, they define a metric. Or if I have fixed orthonormal basis. So Riemannian metrics are ON bundles. This is the main point, and where things start to be actually useful. Then you can more or less guess the following, which are not many details, but it is if I've got a manifold of even dimension, DL and half T structures are the same things, are almost complete structure. Okay, this can be more or less used. And Hermitian matrix, this is probably, you can guess it, Hermitian. Adesso c'è un gesto decente. Allora, Hermitian matrix are UN bundles. Okay, that is the unitary groups preserved Hermitian matrix. This is more or less clear. Now, the relation to holonomy is this. And I have ok, sì. Vedo forse qui ho saltato qualcosa. Ok, no, but okay, I skip just one definition. Okay, let's give this definition. Definition. Connection on TM is compatible with a G structure if the corresponding connection grazie. On the frame bundle reduces to P. This just means that our connection, which is a subbundle of the tangent of F, actually live in the tangent P. Okay, just this. So these are compatibility. Of course, compatibility of the metric is equivalent to compatibility to an ON structure. They're equivalent. And so we can give the relation that this has for holonomy condition. We have a connected manifold. F is the frame bundle. Nabla connection, the tangent. For every Lie group that there exist structures compatible with blah blah if and only if the holonomy of this is contained in the group G. Okay, so holonomy and G structure are connected by this. If I have a restricted holonomy, so I have a group that is smaller than the biggest possible group, say, then I have a compatible G structure automatically. Okay, and so it is the way in which it helps us understanding geometry. There are special bundles with special compatibility with the connection if the holonomy is restricted. Now, to conclude, really, what we need to say is just this. Another last technical lemma, and then we will see why Kähler and Ricci-Platt are equivalent to having special holonomy. Technical lemma, which we won't prove for reason of time, is the following one. As soon as we have a group, which is the stable end representation of GM on some vector space, assume that G stabilizes some vector of V. For this representation, then we have that G structure are in correspondence, are identified by, say, with section sigma of this, so from M of the vector bundle associated, such that sigma dx equal u v or sum u in GL n. Okay, this is just an element on these things, which is a product, GLM times V over a quotient. I'm using this bracket to denote an equivalence relation. Okay, this should be a couple UV, but there is a quotient, so this is an equivalent relation. Okay, these are the components on this product, but there's also a quotient. Moreover, G is compatible if and only if nabla is parallel. This is an important lemma. You have that compatible G structures are identified with parallel section of this new bundle that I gave you. This is the really fundamental tool that we need. Okay, it's not too hard to prove it. We just don't really have the time to discuss it. So maybe another video opportunities. But so we have just, okay, this correspondence between flat sections and compatible G structure, and we can use it to verify that indeed Kähler metric. Remember this. This is something that we saw in Letitia's talk. We saw that if you have an Hermitian metric, this is Kähler. If and only if nabla of J equals 0, where J is the almost complex structure. Okay. You also have seen that the curvature of the charm connection on the canonical bundle is the Ricci form. Okay, with these lemmas together, we'll prove pretty quickly that Kähler and Ricci-Platt-Kähler corresponds to special holonomy. Okay, proposition. Okay, the UM structure given by an Hermitian metric is geometrical if and only if our manifold is Kähler. So geometrical means that, okay, the Levi-Civita, there is a section which is parallel with respect to the Levi-Civita connection. And okay, this is equivalent to say that if then the holonomy group will be contained in UM for what we didn't prove, but we saw. Okay, so this is equivalent to say if the holonomy is contained in UM, then this is Kähler indeed. Okay, proof. This is pretty quick. One can see quickly that these things at the special group are just this group. Why this is important? Because it can be seen easily that this group, being group of complex matrices, which is orthogonal, UM fixes J. Okay, this can be seen easily. So this structure is geometrical. By definition, if and only if nabla J equals 0. Okay, this is a section of the right bundle which are not expliciting, but then if and only if it is Kähler. Okay, this is more or less the idea. And again, for the last part, what we will prove is that being Ricci flat is equivalent to having, is equivalent to having holonomy UM, of what we said before. Then last step, position. We'll only prove it for simply connected manifold because it's easier, but we don't really need assumption. Position M, J, H, simply connected. Kähler is Ricci flat if and only if the holonomy of the Levi-Civita connection is contained in the special unitary group. What's the point? Here we have to use something which is deeper and which we will not prove. But the point is, this thing is 0 if and only if there exists parallel section of, this is the canonical, okay, homomorphic M forms. This is something that we will not prove, okay, this is omitted. But what happens that SUM can be identified as the stabilizer of some element of this. This seems complex, but it's not really hard because these are the same things. These are M forms, which are the same things as volume form. So if you just remember how volume is related to the determinant, you might guess that having determinant 1, the action of UM on this is just multiplication by the determinant, okay? Because this is M4, you're just acting on any component of this form, this is the determinant by definition. But this matrix is determinant 1, so this is of course fixing this space, okay? So it's just recording this space, and then there exists a parallel section, again, of the right bundle, if and only if, okay, the structure is geometrical, because we have seen it before. Okay, so reach zero gives us this parallel section, and we can't really prove this. But one can see that since SUM is indeed the stabilizer zero, this is equivalent to have a compatible SUM structure, indeed, and this concludes more or less the proof. Okay, so we are done. This is more or less everything I wanted to show, and that's it.
Okay, thank you, Filippo. Does anyone have any question? Okay.
Yeah, maybe I have one. But there's nothing that can be said in that proposition, of course, in terms of holonomy, if you drop the Kähler hypothesis, right? Of course, you kind of go away from.
So how did you characterize holonomy? That's what you're asking me.
You kind of go away from Berger classification. I was wondering if there is pretty much such a property if you drop the Kähler hypothesis there.
Well,
if you saw something, of course, it's.
No, I mean, okay, we know which are the Ricci-Flat holonomy groups, so the point is, of course, proving such a destruction in the other possibility, in the sense that we have two that are non-Kähler of Ricci-Flat holonomy group, and we have SON, okay? I don't know if SON can have Ricci-Flat metric that are not flat, of course, or not. That's another point. So the point is, I don't know how, of course, proving how Ricci-Flatness gives some condition of this type for those holonomy groups. So one should study the related bundles, of course.
My question was exactly this, sir. There is a chance that many of those metrics kind of fall into the ON or SON.
I don't know.
Okay.
Are there any other questions?
Okay, great. Thank you very much.